Welcome back to another lecture in space robotics. Today we're going to be talking about the structures and mechanisms subsystem of a space robot. Hopefully by the end of today, you will be able to define the function, typical requirements, design considerations, and verification methods, and survey technologies associated with the structures and mechanisms subsystem. The structures part of the subsystem is to provide mechanical integrity, layout, and support for the spacecraft and its subsystems. Spacecraft structures are organized into three different levels: primary, secondary, and tertiary. For a biological analogy, think bones for primary structures, connective tissue for secondary, and skin or clothing for tertiary. Let's use the Mars 2020 or Perseverance rover as an example. An example of a primary structure is this load-bearing frame that defines the shape and takes all the mission and launch nodes. For Mars 2020, that's the Warm Electronics Box, or WEB, a rugged central chassis made of titanium and aluminum, which houses and protects the avionics, power systems, and onboard computer. It provides the structural backbone for the entire rover. The secondary structures are interfaces that attach subsystems to the primary frame, like brackets, shelves, and mounts. An example is the Mars 2020's mounting struts and brackets for the MASS, which carries SuperCam, the robotic arm interfaces over there, and the suspension components. These structures transmit loads from instruments or appendages to the web while maintaining alignment and stability. The tertiary structure are auxiliary supports that do not bear significant load, such as cable trays, insulation layers, or shielding panels. On Mars 2020, they are the thermal blankets and multi-layer insulation, or MLI, that wrap parts of the rover to regulate temperature, or the covers and shielding panels that protect wiring and sensors from dust and radiation, or also the cable routing trays used to manage and shield electrical harnesses. Now that we've looked at the structural skeleton of space robots, let's shift to the active elements, the mechanisms portion of the subsystem. Mechanisms are the parts of the system that move, deploy, or actuate other components. In contrast to the passive load-bearing role of structures, mechanisms allow the spacecraft to interact with the environment, transform, or transition in between configurations. We define the mechanisms subsystem as the collection of systems responsible for deployment, mobility, actuation, and mechanical control throughout the mission. On Mars 2020, some noticeable mechanisms include the robotic arm all the way over there, the mast mechanisms, the sample caching system, and the wheels in suspension, which are right here. The robotic arm is a multi-jointed arm that deploys to perform science operations like coring and drilling. It has actuators at each joint and an end effector with interchangeable tools. The mast includes a mast deployment mechanism that raises after landing, and it hoists the SuperCam and the navigation cameras. Mechanisms of the sample caching system handle core sample retrieval, storage, and tube sealing, one of the most complex robotic mechanisms ever flown. The rocker bogie suspension and the 6 independently driven wheels provide terrain adaptability. Each wheel has its own drive actuator and some steering actuators. Now here I need to be a little bit more specific about the different roles of the structures and mechanisms subsystem and the guidance navigation control subsystem. Structures is responsible for answering the question, can the wheel physically move when commanded? And the GNC subsystem is responsible for when and how should we command the wheel to move to reach a destination. One of the most fundamental responsibilities of the structures and mechanisms subsystem is to withstand launch and mission loads. This means surviving some of the most extreme mechanical environments a spacecraft will ever experience, particularly during launch. This figure shows a dynamic profile from a typical space shuttle launch, plotting how altitude, velocity, atmospheric density, and dynamic pressure change over time in the first 2 minutes. The black line is the key line to interpret, representing dynamic pressure, which is proportional to 1/2 rho v squared. Notice that around 1 minute into launch, right here, we reach a point labeled max Q. This is where the combination of high velocity and still somewhat dense atmosphere creates maximum aerodynamic stress on the vehicle. This is a critical moment for spacecraft structural integrity. The entire system must survive not just axial launch forces, but also launch and vibrational loads induced by dynamic pressure. On the right, you see a visual of the space shuttle punching through the atmosphere. The condensation and shock waves are visible around the nose due to this pressure buildup. So whether we're launching a rover, lander, orbiter, or uncrewed aerial vehicle, the structure's subsystem must be designed to survive max Q, vibration, shock, and quasi-static loads. Launch has some of the highest loads that shape the structural design of our space robots. In addition to withstanding launch forces, the structures and mechanisms subsystem must protect the spacecraft from harsh environments throughout the mission, including thermal extremes, radiation, and mechanical shocks. On the left, you see a diagram showing the penetration power of different types of radiation: alpha, beta, gamma, and neutrons. Alpha particles can be blocked by just paper or a thin layer of skin. Beta particles can be stopped by materials like aluminum, which is commonly used in spacecraft. Gamma rays and neutrons, however, require much denser shielding, such as lead or even concrete, which are often infeasible for spacecraft due to mass constraints. So spacecraft designers must get creative by layering materials, using internal placement of sensitive electronics, or leveraging multifunctional structures that both support and shield. On the right, you're seeing an amazing image taken by the Mars Descent Imager aboard the Perseverance rover. It shows the heat shield, which had been jettisoned, still tumbling a few meters below the rover as it descended through the Martian atmosphere. That heat shield played a critical role. It protected the rover from temperatures exceeding 1,000 degrees Celsius caused by atmospheric friction. It also helped absorb and distribute the mechanical shock from deceleration forces as the spacecraft slammed into the Martian air at hypersonic speeds. When we talk about structures and mechanisms in space robotics, it's important to remember that the core requirements include mass, volume, stiffness, strength, thermal conductivity. All of these requirements apply to all space robot platforms. But how they're prioritized and solved can vary dramatically. This slide has a depiction of the Mars Ingenuity helicopter demonstrating these various requirements in the helicopter's ultimate design. For mass and volume, Ingenuity had to be incredibly light, just 1.8 kilograms, and compact enough to be stowed underneath the Perseverance rover. Every gram counted, especially for flight in a Martian atmosphere that's only 1% as dense as Earth's. For requirements on stiffness and strength, the carbon fiber rotor blades needed to withstand thousands of RPM with minimal deformation. Likewise, the landing legs had to be strong enough to absorb touchdown forces, but light and compliant enough not to add mass or bounce the craft. For thermal conductivity, nighttime temperatures on Mars dropped to -100 degrees C, so Ingenuity uses an insulated fuselage frame and integrated heaters to survive the night. Structural materials had to manage both mechanical and thermal performance, including aluminum, composite, and foam elements. During deployment, Perseverance dropped a debris shield using a spring-loaded arm to rotate Ingenuity, deployed its landing legs, and lowered it to the surface. These are classic examples of mechanisms working across multiple subsystems, combining actuation, sequencing, and structural interfaces. Let's briefly look at how structural and mechanical requirements specialize by platform, starting with orbiters. For orbiters, one of the biggest constraints is dense packaging for launch. Everything, including deployables like these solar panels, booms, and instruments, must fit inside a payload fairing of the launch vehicle. Take the Juno spacecraft. You can see in this left image here, it's fully deployed with long solar arrays. But in the center, you can see it stowed tightly inside the Atlas V fairing, every component carefully folded in. This drives several structural priorities: compact mass distribution to manage moment of inertia, precise interfaces for deployables that must unfold or extend post-launch, and enough stiffness and strength to survive the violent launch environment in a tightly packed configuration. In summary, for orbiters, structures must be compact, strong, and deployable, all while fitting inside a fairing like the 4.2 or 5.4 meter Atlas V shroud, which you can see all the way over there. What goes up must come down, And for landers, coming down safely is the whole point. This diagram shows the full entry, descent, and landing, or EDL sequence for NASA's InSight lander, which touched down on Mars in 2018. From atmospheric entry at 5,500 meters per second all the way down to the gentle 2.4 meters per second touchdown, every second of this descent involves intense structural and mechanical demands. The structure's subsystem plays a critical role here. The heat shield must survive 1,500 degrees Celsius during entry, then separate cleanly. The landing legs must deploy mid-air, absorb impact energy, and provide stability on unknown terrain. The frame must withstand 7.5 Gs of deceleration, shock loads from parachute deployment, and engine vibration from the final descent burn. This is where landers diverge from orbiters and rovers. Their structures must be shock-tolerant, foldable, and resilient on impact, especially since landing conditions may not be precisely known in advance. So for landers, survivability isn't just about surviving launch, it's also about surviving the fall. On top of surviving launch and landing, once we get to roving, the structural and mechanical design must prioritize terrain adaptability. This image shows the Perseverance rover, and you can clearly see the importance of several aspects. It has high ground clearance to avoid getting stuck on rocks or slopes. It also has high compliance, meaning the suspension can flex and adapt to uneven terrain without overloading the chassis. The rocker bogie suspension system is a classic example, which is seen right here. It allows all 6 wheels to stay in contact with the ground while distributing loads safely across the frame. The structure must also be rigid enough to support heavy instrumentation, like this robotic arm and mast, while still allowing movement over sharp terrain, features, dust, and regolith. Unlike orbiters and landers, rovers must face dynamic, multi-point loading every time they move, and their structure must act more like a walking frame than a stiff shell. UAVs, short for uncrewed aerial vehicles like the Mars Ingenuity helicopter, has to survive launch, landing, and roving, and if it gets to flying, the top priorities for the structural design are low mass and high stiffness. We already covered these in an earlier slide, but here's what makes them absolutely critical for flight. The vehicle must be light enough to generate lift in Mars's thin atmosphere, which is just 1% of Earth's, and at the same time, the rotor blades and fuselage must be stiff enough to avoid deformation at 2,400 RPM. This delicate balance means even small changes in mass or material properties can make or break the mission. So unlike orbiters, which need compact stowage, or rovers, which need ground adaptability, UAVs demand aerospace-grade efficiency in every gram and every strut. What you'll notice here is that the rotors and the legs are made of carbon fiber, which are very low mass for their stiffness and strength. One of the biggest design drivers for structures and mechanisms is payload placement. Because instruments don't just care about surviving launch, they care about where they are on a spacecraft and what they can see. Take Juno, for example. Every payload here you see required specific structural accommodation. Instruments like JunoCam, GRAM, and the Stellar Compass had to be oriented away from the spacecraft body to get a clear field of view. The magnetometers were placed far out on booms to minimize interference, requiring deployable structures and stiff joints. High sensitivity optics and spectrometers needed both line of sight and thermal shielding. Internally, components like batteries and avionics were placed in locations that balanced radiation protection and the spacecraft's center of mass. Payloads are not just bolted on, they dictate where structures must be strong, where mechanisms must move, and how the entire vehicle must be arranged. Geometry is one of the most fundamental constraints that guides structural and mechanical design decisions, and it shows up in different ways across different mission types. Let's start out with form factor constraints. Historically, one of the biggest drivers is that the spacecraft needs to fit within a launch vehicle fairing. For example, the Juno spacecraft in the Atlas V, with its deployable solar panels and booms that unfold in space. That is a packaging problem, but it's also a structural design problem. Next is clearance and deployability, which matters most for rovers and UAVs. Rovers need high ground clearance and articulation to traverse rocky terrain without bottoming out. If an aerial vehicle like Ingenuity is deployed from a rover, it needs enough room to unfold safely and take off without interference. And finally, center of mass and inertia control. This shows up in launch requirements. Your spacecraft must meet strict moment of inertia specifications for dynamic stability. On planetary surfaces, rovers must maintain a low center of mass to avoid tipping. And for UAVs, flight stability and control authority are directly impacted by how well balanced the body is about its rotor axis. So across all platforms, geometry drives the structural envelope, what fits, what clears, and what flies straight. One of the most important responsibilities of the structure's subsystem is to withstand mechanical loads. And these loads come in many different forms. Let's walk through each one and how they show up in different types of space robots. First, static loads. These are steady or slowly varying forces. For example, the body of a satellite supporting its own components in orbit. You'll see these most in orbiters and landers during cruise or idle operations. Next, dynamic loads. These come from fast motions, like when solar panels or booms deploy. We see these in UAVs, rovers, and any spacecraft with moving parts like this orbiter. Thermal loads happen when the spacecraft heats up and cools down. That expansion and contraction causes internal stress. A good example of that is on Mars, cycling between hot days and freezing nights. Fatigue builds up over time in small, repeated stresses, just like bending a paperclip until it snaps. You can see fatigue in the wheel treads over there of Curiosity. This is a big concern for rovers and any long-lived moving part. Impact loads all the way over there are sudden and intense, like when a lander hits the surface. The entire shock transfers through the landing legs. These are also relevant for UAVs during takeoff and landing. Vibration loads come from launch or mechanical systems. Launch is especially brutal. High-frequency vibrations shake every component, so orbiters and payloads must be built to survive that ride. Dynamic pressure is the aerodynamic stress of a vehicle as it climbs through the atmosphere, and it peaks at max Q like we talked about earlier. This is critical for orbiters and landings during ascent and atmospheric entry. Overall, launch loads drive most of the loads for orbiters, shock and impact dominate for landers, mobility and fatigue are central for rovers, and flutter and vibration are key for UAVs. Understanding the load environment across the full mission timeline is what guides a structural engineer. When selecting structural materials for robots, we balance 5 key properties in a material: density, stiffness, strength, ductility, and thermal expansion. Let's walk through this comparison table that I put together a while ago, but still demonstrates many of the key points of performance metrics you want to trade off. First, there's density. Ultimately, the lower the density, the less mass, and the better. The clear winner here is carbon-carbon composite at just 1.6 grams per centimeter cubed, making it ideal for weight-sensitive components like UAV frames or deployable structures. In contrast, stainless steel is heaviest at 8 grams per centimeter cubed. Next, stiffness, or Young's modulus. This controls how much a material deforms under load. The stiffer the material, the more resistant it is to bending and vibration. Stainless steel leads here with 193 gigapascals, followed by titanium and CFRPs depending on fiber direction. Strength comes in 2 forms: tensile yield strength and tensile ultimate strength. For yield strength, this tells us when plastic deformation begins. Titanium is the top performing here at 880 megapascals. For ultimate strength, titanium again wins at 950 megapascals, nearly triple that of aluminum. Ductility describes how much a material can stretch before breaking. This is important for absorbing energy without fracturing. Stainless steel is extremely ductile at 50% strain, while carbon composites are the most brittle, just a few percent strain at failure. Thermal expansion, or coefficient of thermal expansion, CTE, describes how much a material grows with temperature, which matters for tight tolerance structures. Low CTE reduces stress from thermal cycles. Carbon-carbon composites have the lowest CTE, as low as 0.2 micrometers per meter Celsius, which is why they're used in precision instruments and thermal shielding. Let's wrap up with 2 real-world considerations: Outgassing, especially for internal spacecraft materials, can degrade optics or contaminate surfaces. Here, stainless steel 316 has the best vacuum outgassing performance. For cost, aluminum is cheapest at $3.46 per USD. This was taken in 2020, so it might be different now. Whereas titanium offers superior performance in several metrics, but at a premium, nearly $100 for the same part. When designing space hardware, it's not enough to just pick strong materials. We also need to think about how components are joined, manufactured, and how clean they are. These process-related constraints can heavily influence design. Let's start with joining techniques. In this image here, you can see a simulation of a threaded connection, highlighting stress concentrations in a bolted joint. This shows how traditional fasteners can become failure points under cyclic loads or vibration. Still, welding remains one of the strongest methods, but it's not always the best. It's permanent, heat-intensive, hard to inspect, and time-consuming. So while welding can outperform bolted joints in strength, it's used carefully and selectively in high-stake assemblies. Let's talk about manufacturing constraints. On the bottom right, we can see a comparison of traditional versus additive manufacturing processes. Notice how traditional manufacturing becomes more expensive as parts grow more complex. That's the dark gray line. Additive manufacturing, shown in red, handles complexity more efficiently, allowing for lighter, more integrated parts like the bamboo structured bracket shown above. Also note in that figure on the bottom right how tolerances stack up across parts. Even small machining errors can add up when assembling multiple parts in sequence. That's another reason why additive methods, which can print integrated geometries, are gaining popularity in spacecraft design. Lastly, let's address outgassing and cleanliness. In the top image over there, we can see a schematic of a vacuum test chamber setup adapted from NASA's ASTM E595 test. Materials are placed in a chamber, heated to 125 degrees Celsius in vacuum, and any vapors they emit are condensed onto a collector plate for analysis. The timeline graphic shows the stages of the test, from initial weighing to exposure to final weighing. This helps us measure TML, or total mass loss, and CVCM, collected volatile condensable materials. NASA standards are strict, where TML has to be less than 1% and CVCM has to be less than 0.1%. And the reason for that is that even a thin layer of condensed gas can ruin optics or degrade thermal blankets. That's why cleanliness isn't optional. Every component must pass this testing. Designing for space is as much about how you build and assemble things as what you build them from. Another design driver is structural integrity. And when we talk about structural integrity, what we're really asking is, can this part survive the loads it will face with a safety margin? That margin is captured by something called factor of safety. Now you may ask, how do we calculate that? Factor of safety is a ratio of how much a component can take before failure to how much we're actually asking it to take. So it's defined as a failure load divided by a design load, or equivalently, a failure stress divided by a design stress. Let's look at this left image to define one of these terms. This stress-strain curve shows what happens to a material under tension. The blue line is stress versus strain, and at first it stretches elastically, and then we hit this yield strength, the point where permanent deformation happens. Eventually, we reach ultimate tensile strength, which happens at this necking, the peak of the curve. After that, the material fractures. So when we say failure stress, we usually either mean yield strength, if we want to avoid any permanent deformation, or ultimate strength, if we only care about catastrophic failure. Your design will specify which one to use, and your design stress must stay well below it, based on your factor of safety target. Now moving on to this right image, this is a real fastener under a simulated load. The top graph shows how stress over time occurs during cyclic loading generated through finite element analysis, or FEA. That peak point, around 3,400 megapascals, represents the design stress the fastener experiences in deployment or service. Below it, the FEA image shows where that stress concentrates, especially in the threads and the base. If we know the failure stress of the fastener material, let's say 4,000 megapascals, and then we know the design stress of 3,400 pascals, then we know that the factor of safety, if you put 4,000 over 3,400, is 1.18. That's probably too low for aerospace, where we typically want a factor of safety above 1.4, but more typically 2.0, depending on our verification method. So for this particular component, we need to go back to the drawing board and change the geometry or the material or reduce the load. Here are screenshots of the minimum design and test factors for metallic structures and also for fasteners taken from the NASA document called Structural Design and Test Factors for Safety for Spaceflight Hardware, which guides the requirements for structures and mechanisms. As you can see, for different failure modes, the factor of safety varies. We can also see for different testing methods on the far columns, the factor of safety either differs or is not applicable. We need to identify critical loads for each structural component and check that these factors of safety are sufficiently high. When we design space robot structures, it's not enough just to model them or design them. We need to verify that they will survive the conditions of their mission. Earlier, we talked about factor of safety, and we introduced the NASA Structural Design and Test Factors tables that you saw on the last slide. Those tables specify the level of confidence we need to achieve, whether through analysis, test, or both. Now, let's look at some tools that can help us meet those requirements. On the left side of the slide, this is finite element analysis, or a screenshot of some FEA results. Hand calculations like we did before with factor of safety treat the structure as a single element. They're useful when the geometry is simple and the load path is easy to predict. But what if the path is curved, hollow, bolted, or tapered? What if the loads come from multiple different directions or there are complex constraints? In those cases, we use FEA to break the structure into smaller pieces or elements and simulate how they deform together. This helps us understand how local stress patterns add up to global behavior. Now let's move on to the images on the right side of the slide. These show how we verify our designs physically. The top images show tension and compression testing. We pull or push a sample until it yields or breaks. This verifies that the material performs as expected and gives us confidence in our strength margins. Next is vibration testing. Hardware is mounted to a shaker table where we simulate the launch environment. This helps us confirm that the structure can survive high-frequency collisions without resonance or failure. And then right next to that is fatigue testing. This is where we apply repeated loading to a part over tens or hundreds of thousands of cycles. We use this for components like rover wheels, joints, and deployment hinges, which experience repeated stress during their mission. The thermal vacuum chamber replicates the space environment. We test structures under vacuum and extreme thermal cycling to simulate the effects of orbit. Thermal strain, contraction, and expansion must all be accounted for. And finally, you see verification methods like deployment testing. Here, NASA engineers are unfolding the Juno spacecraft solar panels in a clean room with gravity offloading. This ensures that every hinge, latch, and panel deploys exactly as intended once in space. It may sound simple, but even one stuck hinge could end the mission. Together, analysis and testing from FEA to vibration and deployment give us a full picture of structural integrity. They help us not only meet the required factor of safety, but actually prove that our designs will work in the real conditions of space. When we send a robot into space, yes, we have to move, deploy, or carry instruments, but we also need to protect it from the harshness of its environment. The structures and mechanisms subsystem plays a key role in shielding a system from damage. Let's look at a few of the most important environmental threats and how we design them around them. First, radiation shielding. High-energy particles, especially near planets like Jupiter, can fry electronics. On the top left of this slide, you see the microwave radiometer payload on the Juno spacecraft. Its electronics are placed inside a thick radiation vault, shown here in gold, to block incoming particles. This is especially critical for long-duration missions with sensitive instruments. Next, we deal with hazards like dust and abrasion, which are especially dangerous on the Moon and Mars. Sharp regolith particles can wear down seals, gears, and expose linkages. In the bottom right corner, you can see a spring-loaded Teflon seal that was tested to protect robotic joints. These seals were run through 10,000 cycles with Lunar Simulate, and the tests showed they were successfully able to keep dust out without wearing down the shaft. That seal was used on a Mars rover at a joint on its robotic arm. The robotic arm structure has to be tough, but the instrument deck and camera systems are especially vulnerable. That's why they're recessed, covered, or shielded using smart material layering. Not only does the entire structure need to be tough and the joint has to be protected, but the instrument deck and camera systems are especially vulnerable to dust and abrasion as well. That's why they are recessed, covered, or shielded using smart material layering. And finally, we use thermal insulation to survive the cold. Here, you'll see a NASA technician integrating insulation onto the Ingenuity helicopter, which operates in Martian nights that drop below -100 degrees Celsius. Its electronics are housed in a small silver box called the H-Web, or Helicopter Warm Electronics Box. This box uses Kapton heaters and a metallic Kapton film to both absorb solar radiation and trap heat inside the avionics compartment. Whether it's shielding from radiation, sealing out dust, or retaining heat, the Structures and Mechanisms team is responsible for building the physical buffer that keeps the rest of the spacecraft safe. As we close this submodule on structures and mechanisms, it's important to talk about design philosophy moving forward. That's the mindset that we bring when building systems that have to survive space. The first guiding principle is design for extremes. Space robots operate under the most unforgiving conditions, from violent launches to freezing nights on the Moon or Mars. So mechanical robustness isn't just ideal, it's required. The images on this slide show exactly why. On the left, you see the disintegration of a Falcon 9 during ascent. That spurred an investigation that traced the initiating cause to a failed axial strut, which you can see here. This strut was holding a pressurized helium bottle inside the second stage oxygen tank. When the rod end fractured under load, the bottle broke free, accelerated upward due to buoyancy, and slammed into the top dome of the tank, causing catastrophic failure. It's a powerful reminder that even one small component can bring down an entire vehicle if it's not designed for the full range of conditions. That brings us to our second principle, to balance mass, strength, and function. You see that illustrated in this multi-dimensional axes. Every structure has to achieve its purpose, but also stay as light as possible and strong enough to survive. Design is always a trade-off between these three axes, at least. The third principle I want to impart is to design with modularity, adaptability, and test access. We want systems that can be verified, maintained, or repaired, especially for high-wear components. An example comes from this story about jack screws used throughout the Kennedy Space Center. Historically, these screws relied on a single soft nut that wore down over time. If it failed without being noticed, it could lead to catastrophic collapse. So engineers designed a fail-safe jack screw with a secondary follower nut that would automatically take over if the primary one failed. It included mechanical and electronic wear indicators so technicians could spot the problem before it became mission-ending. This type of redundant, inspectable design is key to structural integrity. To summarize, designing structures and mechanisms for space is about more than picking strong materials or analyzing stresses. It's also about anticipating failure modes, balancing competing demands, and building in the ability to test, monitor, and adapt. That's what it means to design for extremes and to design for success. So hopefully, you can now define function, typical requirements, design considerations, and verification methods, but also survey various technologies associated with these structures and mechanisms subsystem. Thanks for tuning in.